Good morning. We'll get started here today. So we have a couple problems still from chapter 3, 2 in the notes that we're doing, and then we'll do some review problems. There's a review packet that I posted of problems that I'll be working on today and Wednesday in class. There's a few slides on study skills, but I'm not sure. I think we may hold off until Wednesday to talk about those things so we can spend today mostly reviewing problems. I might just kind of quickly flow through the slides today so you can get a sense of a few last study habits to try to put into place before our Wednesday night exam. So again, just a reminder, if you have a conflict with Wednesday's evening exam, 6:30 start time, if you have bio lab, physics lab, some other class, some sort of university event taking place, look at the exam attendance policy. Very end of it is a form that you can fill out. And then you can do this for the other midterms too. So if you have looking ahead to midterms 2 and 3, they're also Wednesday night exams, same time. The final exam is a different time slot. So the final exam is a morning exam. I think Monday, 8 a.m. of finals week. But you can check the syllabus for that information. But check the exam attendance policy if you need to submit any exam requests for alternate times or makeups. So for this reaction here, we have barium, nitrogen reacting to form Ba. This is barium if we're thinking of naming. And the common ion of barium in the calcium group would be 2+. Common charge of nitrogen would be a 3-. So this is barium 2+, nitrogen 3-. So this would be barium nitride. In terms of naming. But in terms of balancing the reaction, we just need a 3 and then a 1 and a 1 work. So 3 bariums, 1 N2 gives us 1 Ba3N2. Whenever we're given moles, the problem is pretty straightforward, I think, to determine the limiting versus excess reactant. Some problems will just give you grams instead of moles, and you can turn it into the problem of having moles just by converting grams to moles, or we can set up dimensional analysis steps, or we can set up a chart. We always have options with stoichiometry problems. Hopefully all those options make sense. We might look at a few different ways of solving problems as we go throughout the lecture today. But I think for this problem here, we can see we're supposed to have a 3-to-1 ratio of barium to nitrogen, and we have given a 3-to-2 ratio. We have more nitrogen present than we really need in this reaction. So just by inspection of the fact that I have 2 moles here, and I only needed 1. I only need 1 mole of nitrogen to react with 3 moles of barium, so the nitrogen is in excess. And then the barium is going to be my limiting reactant. The limiting reactant, of course, is the one completely consumed in the reaction. So once I produce as much product as possible, I've lost all the barium, and I will have lost 1 mole of nitrogen. And so the barium goes to 0, and then the nitrogen goes to 1 mole. And if I'm not sure that it's 1 mole, I could always maybe solve a dimensional analysis step. I could say something like how many moles of N2 react with the given amount of barium. So I could solve this problem here. According to the coefficients, for every 3 moles of barium that react, 1 mole of nitrogen has to react with it. In the down arrow, I'm just kind of thinking one reactant is consumed while the other reactant is consumed as well. And so what I'm calculating here is the amount of nitrogen that is lost in the reaction. And that works out to be 1 mole. And of course, there are 2 moles to begin with, so there's still 1 mole after and 1 mole consumed in this particular reaction. I could have mixed together 3 moles of each, let's say. I can mix together whatever ratio of these 2 reactants I want. There's nothing about the reaction that says I have to mix 3-to-1. The ratio in the reaction says if the reaction occurs, that's the reacting ratios, 3 bariums to 1 N2. But I can mix together whatever concoction I wish to mix together. If I instead had mixed 3.0 moles of N2 with the same number of barium, then of course I'd have 2 moles remaining after the reaction. I'd still have 1 mole of nitrogen consumed. The key is really making sure you see the difference between when you calculate the nitrogen that's been consumed versus the nitrogen that remains. The nitrogen that remains is the initial minus the amount that was lost. So it's the 2 moles initial minus the 1 mole consumed. So we have 1 mole remaining. And then if we're reacting to form, yes?
When you did the conversion, what was found as that what's remaining or what you subtracted from the addition?
Well, so what we find here is the amount that was lost. So for 3 moles of barium to react, 1 mole of nitrogen reacts with it. So whenever 3 moles of barium react, we also form 1 mole of barium nitride, according to the reaction. And so the reaction should produce a mole of barium nitride. So our yield of the reaction should be 1 mole of barium nitride. And that's the product forming. So we form a mole of product, we've lost all of our barium, and we've lost half of the nitrogen that happened to be present. And so then if we're asked, well, if only 0.75 moles of barium nitride forms, what's the yield of the reaction? I think you can very easily see with these numbers, it's pretty easy to calculate the yield 75%, but our percent yield is just our actual yield divided by our theoretical yield, the maximum yield we were supposed to get according to the stoichiometry, times 100%. So we got 75% of the yield in this particular case from what we were supposed to get. Whenever we give you grams instead of moles, the problem's the same. It's just we get the extra step of gram to mole conversions using molar masses, and we might have to look those up. So by putting, if we say you have 5 grams of barium and 10 grams of N2, how much product can form? It's the same problem. It's just either we're converting to moles and inspecting and thinking about our ratios, or we're just using dimensional analysis and some thought trying to figure out which of those 2 reactants is limiting versus excess. If we're given the product yield, if we had said here instead of 75 moles of barium, if we had said, 100 grams of barium forms, what's the yield? Well, we'd have to convert that to moles, or we'd have to convert our 1 mole yield to grams. So we can take and divide either moles by moles of the product or grams by grams. So whenever we're working on a percent yield, the yield can be in grams, it can be in moles. We just want the units to be the same for both the yields, the actual yield and the theoretical yield. Well, I would, like the yield versus the percent yield, so you could perhaps say it's 0.75 is the yield in terms of a fraction. That would be a fair answer to this question. I think just more commonly we tend to just use percent yield. So even though I didn't write percent yield out into the problem, you'll see the word yield used a lot, and it's often just given in percentages. So even if you think the answer is a fraction of 0.75, 75% is still that fraction. They're still the same number, even though one's just a percentage. But a fraction versus a percentage are really representing the same value. Does that make sense? Okay, and so then if this yield is characteristic of the reaction, meaning every time we carry this reaction out, let's say we get 75% yield. So if this yield is just some characteristic property of the reaction, then how much barium should be reacted with an excess of nitrogen if we want to yield out 75 moles of barium nitride? Yes? What's that? Yeah, for the last one. Yeah, so what we want to kind of realize in the last one is if we really want to make 75 moles of barium nitride, we're going to have to try to make 100. So we're going to have to shoot for that 75% yield. So if our percent yield, the equation, just reminding ourselves, it's the actual yield that we get or that we want divided by the maximum or the theoretical yield, times 100%, that in this problem here, we're saying we want the actual yield to be 75 moles. So if we actually want to produce 75 moles, we're going to have to try to shoot theoretically for a higher target. This problem is very synonymous with a problem that, if you want to make $75 a week, you of course don't want to just figure out how many hours do I need to work to make $75. You need to think, well, I have to pay taxes. So 75% of my paycheck is what I get to keep. 25% is lost to, say, taxes, so you need to try to make $100. Same thing with this reaction here. So we're going to need to try to make 100 moles. So if our yield of this reaction's characteristic is 75%, and so then we actually want to get 75 moles, 75.0. I'm going to divide and change this into the fraction so I can get rid of the times 100% and the percentage. So 75 divided by the theoretical yield is equal to 0.75 in terms of the fraction of the ratio. So my theoretical yield, just doing some math, is going to be 75 divided by 0.75. So the theoretical yield of the product that we're shooting for just doing the algebra, I'm just making sure that's 100. I'm sure it is. I mentioned before, whenever you're looking at math on a sheet, it always seems obvious, except for when you're holding the pen in front of a room of people. But yeah, that's 100 moles. To 2 sig figs, I guess, if we're tracking sig figs, because our yield was only good to 2 sig figs here, because we had 2 sig figs here. So we'll get 100 moles of what we're trying to shoot for to 2 significant figures. But the problem is asking how much barium we need, not how much product we needed to try to make. So if I want to make 100 moles of the barium nitride, we just then need to follow our stoichiometry back to figure out how many moles of barium we need to start with. So the number of moles of barium are what we want to find, because it says in the problem, how much barium should be reacted. I'm trying to make 100 moles of barium nitride. Well, for every 1 mole of barium nitride, we need to start with 3 moles of barium. Just that coefficient of 3 in front of barium in our reaction, a 3-to-1 ratio. And so that's going to lead us to 300 moles of barium. So we react 300 moles of barium with an excess of nitrogen. Goes in a 3-to-1 ratio. For every 3 bariums, I get 1 Ba3N2. I should get 100 moles, but I only get 75 due to the 75% yield. So it just kind of shows you that whenever you're doing this step here, that the theoretical yield is the one that we're getting or using in a dimensional analysis or in a stoichiometry problem. The percent yield versus the actual yield is just what we actually get. You know, it's just something we get in the lab. We have to go do an experiment or get some information to relate our, from our theoretical yield to the actual yield, what that is with the percent yield of the reaction. And so, just again, the maximum yield is the yield we get for a reaction following the stoichiometry, and then the actual yield is just whatever we get in the laboratory. You can never really look at a reaction and know its percent yield. In this problem here, we were given information that allowed us to know what the percent yield was. So in terms of the notes, I just had one more question, which kind of comes back and circles back around to like a particle diagram question. Because we sort of start stoichiometry problems with these, and then sometimes we get away from a particle diagram question. And I like us to kind of circle back and look at one once we've kind of finished the chapter. And so this problem here, this is actually an old test question. This is one that generally has given students a tough time over years. Let me zoom in a little bit more on this. And so consider the reaction between nitrogen, represented by the black spheres, and oxygen represented by the gray spheres. And the reaction is N2 plus 2O2 goes to 2NO2. So this is the chemical reaction that's occurring. And again, even though the reaction says you should have a 1-to-2 ratio of nitrogen to oxygen, we can mix together whatever proportion of nitrogen and oxygen we wish. And so this is the N2 from what we're told. So the N2 are the black spheres, and then O2 are the gray spheres. And so now whenever you see a problem like this, you can count, you can do math, you can set up charts, you can still do all the tools that we had shown previously. So like if we're counting here, I get 1, 2, 3, 4 N2s, and I get 1, 2, 3, 4, 5, 6 O2s. I don't like to think of this as a reaction like this. I don't like to try to figure out how I would write a reaction for these. I don't like to do that. I like to just think of the reaction here in the ratio that it says for every 1 N2, I need twice as many oxygens. So if I have 4 N2s that would react, I would need double that. I would need 8 oxygens. I clearly don't have 8 oxygens. So nitrogen's not going to be fully consumed. So I've already, just by a real simple thought of noting how many there are, thinking about the reaction, not trying to set up some new reaction with different coefficients. That would, I think, lead us to a confused problem on how we would solve this. We're just looking at our amounts, figuring out if I have 4 N2s react, that we're going to need 8 O2s to react with them. And I don't have 8, I only have 6. Likewise, for all 6 O2s to react, for every 2 of them, I need 1 nitrogen. So if I divide by 2, I get 3. So I only need 3 nitrogens to react with the 6 oxygens. So I can have sort of 1 N2, 2 O2s react. And then on the product side, what we would have for them are 2 NO2. So I'd have an N, let me do it like this. I'd have the nitrogen atom, and then I'd have the 2 oxygen atoms attached to it. Then I have another nitrogen atom for the other 2. So these are gone, been replaced by 2 NO2s. So I do it again, take a nitrogen, 2 O2s, and they're replaced, get a nitrogen, O2, another nitrogen, and O2, and then do it one more time. So I get one more set of 2 NO2s. So I get 6 NO2s forming, and then as you can see, we have that 1 N2 molecule left over. So I can lasso out the reactants and products and make the proper number of products. I could also have just looked and said, well, if 6 O2s are reacting, because we identified that this was the limiting reactant, if all 6 react, for every 2 oxygens that I react, I get 2 NO2s, so I should get 6 just by looking at the dimensional analysis and looking at the math and the problem. So I should have gotten 6 NO2s, and the remaining, let me switch the color back. And so let's make sure we write in our, whoops, forgot to switch the color. So we still have the 1 N2 that's left. After that reaction completes. So I started with the 4 N2s, the 6 O2s. I still end up with the same number of nitrogen atoms, the same number of oxygen atoms, just where we changed the form of some of them. We changed the chemical bonding environment by making our product NO2s. So we get 6 NO2s and 1 N2 from this reaction here. And again, a lot of ways to think about it. You can literally picture it. You have to make sure to picture that remaining N2 that's left over, because it doesn't just disappear. And what we're seeing in a particle diagram question is like a before and after snapshot. And so we're making sure that we see the products that are formed versus the limiting reactants that are left over. Or excuse me, with the excess reactants that are left over. Limiting reactant completely consumed. Okay, so hopefully we have tools available for solving stoichiometry problems. These slides, I think I'll go through these a little bit more in detail later. Metacognition is just the way you think about your own learning. It's sort of having the thought of, I don't understand sig fig, so I'm going to go read about sig figs in the book and try to solve some more problems. It's like that level of detail of thinking about the skills or the problems that you're struggling with and the content you need to learn to help you through those problems, and just being aware of that part of the learning process. Instead of just being a passive observer of information and trying to just apply the things you've seen, it's just trying to make sure you learn the content and then perfect or have practice doing the applications. Yes? No, I don't think so. So in terms of the test, like, will you be required to use a BCA chart or some particular method to solve the problem? I don't think so. There are even some problems I can think of that almost give you a BCA chart that you don't even have to use a BCA chart for. You can just like turn that into a dimensional analysis problem if that's an easier way in your mind to solve the problem. So I think hopefully they all make sense, and it becomes either which way is fastest if you're savvy to solve the problem, or just which way can you get the right answer. Like, we don't need to split hairs. If you're going to have to do a problem, if you need to write out a bunch of dimensional analysis steps to get the right answer, write them out. If it takes you a couple extra minutes, we just got to get faster on some of the other questions. I think the test will have about 25 to 30, mostly multiple choice questions, a couple short answers. The practice exams have some short answer where you're numerically entering a number, or usually the short answer questions. I don't think there's ever been a text enter short answer question. It's always like a numerical data problem. So like a math problem where you're trying to find a number and just keying in your result at the end of the problem. Probably about 5 of those or 6 of those type of questions that you're keying in a number and the remainder of the questions just ordinary multiple choice questions. So just in terms of what to expect on the exam. So like I said, I think I'll circle back and talk about some of these things in more detail on class on Wednesday, but the study cycle that we'll talk a little bit about is something we've already talked about before, where it's like if you could preview some of the topics before class, the reading assignments kind of show you what we're covering so you're able to do that. Then obviously attend class. I don't have to tell you guys, you're already here. If you're watching this online later, come to class. I think it's worthwhile to be here to sit next to your classmates, especially when I give you guys a chance to work on a problem together. I think that's one of the great values of being in a big class like this, is having a bunch of classmates to work with. And then reviewing after class, working problems, and really just getting good at doing problems, closed book, closed note, closed internet. And like the more you do that, the better. The more we're doing problems, just trying to look them up on the test, we're gonna wanna look up how to do everything. We gotta like train our minds to be able to do problems. Even the ones that seem easy sometimes, you take away all the available resources that you may be using with your studying, problems become a lot harder. But if you're practicing without those resources, I think you'll be ready to go. This just shows you that if you're going to learn at a high level, you have to start at the bottom. You have to learn some basic concepts first. You can't just jump into a really hard problem at the end of the chapter. Like if you look at those end of chapter exercises, a lot of times you can't just go do problem number 102 as your first problem. You have to start with problem 1, because you have to start with learning the content, the simple applications, and building up to doing more complex problems. I don't think our tests, like some classes teach here, and then the homeworks are here, and then the tests are here. I don't think we do that in chemistry. I think most of our lecture questions and test questions are kind of all in the middle. Like we're trying to show you the applications and the big problems that we're really trying to get you to do on exams. So I think most of the type of problems you've seen in class are the type of problems you're going to see on the test. Those are the same type of problems you'll see on the daily quizzes, on the homework sets, and on like the practice exams. So I don't think too much should surprise you. There's usually like one weird question that somebody wrote that's kind of off the wall, but there might be one goofy question from time to time that catches people off guard. Even on the practice midterms, you might have noticed that there's 1 or 2 questions that you're like, where did that come from? Don't worry so much about those problems, just worry about what went into it is usually just a couple simple thoughts, or a couple simple ideas being used to solve them. So think more about the content that goes into those problems that helps you get the right answer, more than trying to think about some analog of those questions. So there might be a question or 2 on the test that you guys find challenging. Try not to have that question wreck your test. You can go back on questions, so if you see a question you don't know how to do, skip it, come back to it later. I think having a strategy of not necessarily skipping the long problems, because some problems take a little bit longer to solve, but try to maybe skip the ones you just don't know how to do. Like you read the question, you're like, I don't know what to do. That's a good one to circle and come back to later. You'll get a sample paper booklet that you can write onto during the test, so you can have an actual sheet of paper since you're taking the test on Carmen. You'll have a sample booklet that you can write work onto. We collect it at the end just so that you guys can't write the questions down or share questions with people who might take the test at the alternate test later in the week. But so you'll have a booklet where you can write stuff down. You can easily write down, go back to question 10. Everybody's going to see questions in a different order. It's a randomized order test, randomized answers and things like that. So everybody's going to be working through the test in a different order. So some of you might get a hard question first, maybe last. And by hard, I mean just a problem you individually can't do. And I think everybody in the room will disagree on which problem's the hardest too. So I think everyone will have a problem that they just read and don't understand what to do. Well, just make sure that you don't spend 5 minutes on that problem. Or if you do, it's the 5 minutes at the end of the test. Okay, so we've mentioned the Make It Stick book before. There's another book called Teaching Yourself How to Learn. This book here is about more metacognition topics. The other book's about more just getting practice doing problems with the closed book. So the whole idea of multiple repetitive quizzing is kind of from this book here. I think if you employ those strategies, you'll do very well. But then if you're also in tune with checking your answers and figuring out what you're missing and why you're missing it and learning and filling in those gaps, that's where kind of this book comes into play. Okay. I just wanted to say a few things about that, and I think we'll circle back maybe the end of class on Wednesday and say a few more details about study habits and study skills. But in general, I think you guys are probably pretty well prepared from high school. I think the only difference between like our midterm coming up and a lot of tests you saw in high school is just chapters 1 through 3. It's a cumulative test, and we're like testing you on everything. And I don't know how often high school has like a 3-chapter test where you're really had that material taught in like literally 9 or 10 lectures with a little bit of review, and then you're responsible for everything, or for most of the content of those chapters. So I think the content, the level of detail is very similar from high school. I hope a lot of you guys have seen that chapters 1 through 3, not a lot of difference from, you've probably seen a lot of those topics before. It's just the rigor and the test will be comprehensive. That's really, I think, the biggest difference. Okay, so let's look at some review problems. The first one here, a compound has a molecular weight 4 times its empirical formula mass. It has a composition of 88.8% carbon, 11.2% hydrogen by mass. What's the molecular formula of this compound? Well, remember the percent mass gets us the empirical formula. So from this data here, we can get the empirical formula, the simplest ratio. Once we get the empirical formula, the molecular weight is 4 times that. So we're going to quadruple all the coefficients, or all the subscripts for the C and the H that we might get from our percent mass analysis. So the way I'm going to work out the empirical formula is by taking a ratio of the masses of carbon to hydrogen that's representative and true for the sample. The easiest ratio that I can come up with is going to be 88 grams of carbon present in ratio for every 11.2 grams of hydrogen. And if the empirical formula is a ratio of the atoms in the formula, the simplest whole number ratio of atoms, it's also the simplest whole number ratio of the moles of the elements in the compound. So if I simply convert grams to moles, then I get a ratio. I like to still think of the ratio of the mass. We get a ratio of the moles of these elements. So 7.39 moles of carbon present in ratio in this compound for every 11.1 moles of hydrogen. Now do you see how it's too far off to round to C7H11. Like we can't do that because this is way too big. We need to be within about plus or minus 0.03, maybe a smidge higher. 0.03 to 0.05-ish is about as great as we're ever going to want to round. And so since I can't round, what I'm going to do is use the simple approach. Let's divide by the smallest one. We have to divide both, of course, by the same number, otherwise we destroy the ratio. So if this is a ratio, and I divide one by 7.39, the other by like 11.1, I've broken the ratio. So I have to divide both by the same number. And if I want to get at least one whole number, I get at least one whole number here, because obviously 7.39 divided by itself is 1 mole of carbon. And so this works out to be, I think, pretty clear on what we're going to do next. I get 1 mole of carbon to 1.5 moles of hydrogen. What I need to find is the simplest whole number ratio. I need to start thinking, do I need to double, triple, quadruple? And you could even think on the simplest level, do we multiply by 1? No, because we can't round with 1. So obviously we're not keeping these coefficients. Then we think times 2, and that's going to work. If I double both coefficients, I get 2 and 3. So I get 2 moles of carbon present for every 3 moles of hydrogen. So C2H3 would be the empirical formula. And then we were told the molecular formula is 4 times the molecular weight of the formula weight of the empirical formula. So it would be C 2 times 4, H 3 times 4. So we got to quadruple both of them to keep the ratio intact. So it should be C8, H12. So I don't think we had actually gotten a problem where we hadn't had whole numbers come out at this step here, but if we don't get a whole number when we divide by the smallest number, we should have a multiple. It's going, just start small, don't start big. So start with the smallest, go times 1, times 2, times 3, times 4. As long as it's not like sucrose. I once did an example of sucrose, which has the formula C12H22O11. I once did, if you do the percent C, percent H, and percent O in this, work it out, you end up having to multiply all the moles in this step here by like 11 or 10 or something. Like it becomes a really weird problem actually. but we're not going to give you sucrose. You know, like sucrose or molecules like that, where you have to have a really big multiple. Like if you keep going not times 2, but 3 times 4, it gets a little tricky. And if your numbers in math isn't dead on, you may miss it. But I think, like I mentioned this before, whenever you need to multiply by a multiple, you're going to see these numbers work out to 1.5 or 1.33 or 1.25. You'll pretty easily see if you need to double, quadruple the numbers from the math. Okay, so let's look at number 2 here. So we have a compound, has a formula XCl3 where X is an unknown element. And if the compound is found to contain 79.8% chlorine by mass, what is the atomic weight and identity of X? Okay, so X from the choices you can see are just some element. So is it aluminum chloride, beryllium chloride, et cetera, or one of those other compounds? Well, the way we can figure this out is just through the use of what percent chlorine is, or what the percent composition of a given element in a molecule or compound would be, is the number of that atom in the formula. So there's 3 chlorines in this compound. Let me actually leave this general first. Let me write the percent chlorine in a compound as the mass of Cl in the compound divided by the formula weight of the compound times 100%. And the mass of chlorine in this particular compound will be 3 times the atomic weight of chlorine. Because we know from the formula there's 3 chlorine atoms. So if we know 3 times 35.45, and we can use AMU or grams per mole. It doesn't matter at all. I'm going to use AMU because then our formula weight, we're just thinking about this value here in units of AMU. AMU just coming from adding up the atomic weights of whatever X works out to be in the 3 chlorines. So 3 times the atomic weight of chlorine divided by whatever the formula weight of this compound is times 100% has to be equal to that 79.8% value, because this 79.8% is the percent chlorine in the sample. And so if we do that thing we did earlier, which is get rid of the 100% just to clarify the math a little bit. So let's turn this into 0.798 just to get rid of the times 100%. So I have 0.798 is equal to 3 times 35.45 divided by the formula weight. So all I really want to do here is cross multiply both sides by the formula weight and divide by 0.798 to work this out to find the formula weight of the compound. So the formula weight in AMU is going to be equal to 3 times 35.45 AMU divided by 0.798. And now let me say one quick thing though, and that is the one thought that maybe was missed is if I knew the formula weight of the compound, I could subtract off the 3 chlorines to figure out what X is. So you may be sitting there thinking, or if you thought this was a problem, how does knowing the formula weight help us identify X? Well, if we can figure out what the formula weight of the compound is, I can subtract the 3 chlorine masses and be left with whatever the atomic weight of X is. And so when I get my atomic weight here, is 133.2 AMU. My thought is, well, if I can just subtract the mass of those 3 chlorines, I'm left with X. So if the formula is XCl3, if I take 133.2 AMU minus 3 times 35.45, that's going to be the mass of X. And by mass, maybe more appropriately, the atomic weight of X. So we do 133.2 minus 35.45 times 3 is 26.9 AMU. And so then we just go to the periodic table to figure out now is X beryllium, aluminum, germanium, or gallium, whatever the choices were, or scandium. And we see that the atomic weight matches for aluminum, 26.9. And so we're scanning the periodic table to see what atomic weight is consistent with that molar mass. And the other atomic weights are shown here. They're not 26.9. And so this compound here would just be aluminum chloride. Now you could double check at the end. You could say, you can actually double check this. I'll get your question in 1 second. You could have almost looked at this question a slightly different way. You could have said, well, I only have 4 choices. It's either aluminum chloride, it's beryllium chloride, gallium chloride, or scandium chloride. And we could go calculate the percent chloride for all of those. And we could have calculated that the percent chloride would only match for the aluminum. Yeah.
I was just going to ask, because aluminum has the 3+ chart, CL has the minus chart, would that be another way that you could double check? I know gallium is also on there, but would that be a way that you could double check your answer and check the atoms to see if they balance out what they got?
Yeah, I mean, the beryllium doesn't make sense because beryllium would be beryllium Cl2 if you were thinking about beryllium being kind of in the magnesium group. So it wouldn't make sense it would form such a compound. So in some ways, you might be able to rule answers out that way. You could also say, well, if X was only 9.2 AMU, that the percent chlorine would have been even higher. So like you can almost look at your choices and go recalculate and kind of see. So when you have a multiple choice test, numerical answers that you can solve the problem a variety of ways. You can solve it going forward like we did, or you can look at your choices and go by process of elimination and try to eliminate some answers various ways. And so sodium chlorine react to form NaCl, 23 grams of sodium, 70.9 grams of Cl2 fully react together. So balance the reaction and determine the mass of sodium chloride. Now, one way I've seen students make a mistake on this problem is, well, this is a combination reaction, right? So we're just combining sodium and chlorine to make NaCl. And let's say you don't even bother balancing. You're just looking at this going, well, if I take this plus this, wouldn't the mass of the NaCl just be those two masses added together? It's a combination reaction of combining two elements, so the answer has to be 23 plus 70.9. But that's the wrong answer. Or it might not be the right answer. I can only add these two masses up if those masses correspond to the proper ratio of sodium and chlorine that react according to the reaction, which if we balance it would be 2 and 2. So 2 sodiums and a chlorine molecule reacting together to form NaCl. If I happen to mix together a ratio of 2 moles of sodium for every 1 mole of chlorine, and that's what the masses represent, then I can just add them up. But if one of those reactants is in excess, then it's not going to make its way into the NaCl product. I can't just simply add these up. So this problem here, and a lot of problems that require you to figure out limiting versus excess reactant won't say so. They'll expect you to know that you have to evaluate limiting versus excess reactant. So if we have a limiting reactant here and an excess reactant, we have to go figure it out. And we have to check into the problem to see if we have a limiting versus excess reactant problem. Let me go through this 2 different ways. Let me go through it the dimensional analysis way. I think if we're being asked for how much product forms, this question here is going to be pretty easily solved if I just evaluate the grams of sodium chloride I can form consuming both of the reactants. So if I consume all of the sodium, how much product could I make? And then if I consume all of the chlorine, then how much product could I make? So let's just do the sodium first. And then we're going to evaluate whichever one makes less, because whenever I make the less product with that one reactant, I've consumed that reactant, I won't have enough to make the greater quantity. So sodium is about 23.00 grams per mole. According to the reaction, for every 2 moles of sodium, we produce 2 moles of NaCl. And 1 mole of NaCl has a molar mass of 23 plus 35.45, about 58.45 grams. So 58.45. So then if we consume all the chlorine, so chlorine's 35.45 times 2, so it's about 70.90 grams per mole. But the reaction's 1 mole of chlorine, when it reacts, produces 2 moles of NaCl. And then molar mass of NaCl is the same, 58.45 grams per mole. I'll write that out just so that you have it twice. So we're going grams of chlorine to moles of chlorine to moles of sodium chloride to mass of that product. So this is going to work out to be 2 times the molar mass. 2 times 58.45 is 116.9. So the reason why we can't make this mass here is because at the point at which we made 58.45 grams of sodium chloride, I've run out of sodium. So my sodium's gone. I've consumed the sodium, and I've produced the NaCl. And likewise, when I'm trying to consume the chlorine, I'm producing the sodium chloride. I can't get to the 116. Once I get to 58.45 grams of product, rounding to 3 sig figs, 58.5 grams of product, I've run out of sodium as the limiting reactant. So we've identified here sodium is the limiting reactant, and then chlorine here must be the excess reactant. The problem wasn't asking for how much the excess reactant remains, so I don't have to go figure out how much of it is consumed. Obviously, half of it's consumed if you think about the way the math's given in the problem. So that's how I would use dimensional analysis to solve this problem. So the answer to the question would be 58.45 or 58.5 grams of product forms. Now, one other way I can roll out the 116. So if you look at this problem, you say, well, I still think you might be able to get 116, and this math is crazy. I don't understand it. Well, think about how you started with 23 grams and 70.9. If we just add those two together, like there's no way I can get more than 93.9 grams of product, period, because that's the mass of the two reactants we're adding together. So there's like no way we can create mass. And it turns out that once we get to 58.45, we'll have the difference in mass between the 93.9 and 58.45. So the difference of the mass of the two added together versus the product will be the mass of the chlorine that's left over. So in other words, when we carry the reaction out, we're not creating or destroying mass. If you take the product mass plus the mass of the chlorine that remains afterwards, that should equal what we started with in terms of the two reactants. Okay, so I mentioned we could do this problem 2 different ways. Let me make a little bit more room here and do a BCA chart. Oops, me. So 2Na plus Cl2 goes to NaCl, 2 of them. So if we want to use a BCA chart, and one thing with the BCA chart is I want to plug moles in here, or molecules. So I want to plug in whatever the reacting unit is. The coefficients are either the moles or the molecules of the reactants. And so this problem here being in big quantities of moles is one that's going to make more sense. We could plug into molecules and those like particle diagram questions if we want to use a BCA chart. But we want to use the reacting unit. So we don't just want to plug in the grams here. We want to plug in moles. And so if we convert sodium to moles, it's 1 mole of sodium. And if we convert to 70.90 grams per mole of sodium, this happens to correspond to 1 mole as well. So this corresponds to 1 mole of chlorine. This corresponds to 1 mole of sodium. It's just their molar masses are 23 and 70.90. And so if we had worked out right off the bat those moles, if we just converted to moles and wrote down in our chart, I think you can kind of see the way the math's playing out here, where if we consume all the chlorine down to 0, I need 2 moles of sodium. Can't do that. So this can't happen here. But so if I consume this one down to 0, so if I have minus 2x minus x plus 2x, if I'm consuming the sodium down to 0, and this is my limiting reactant here, what's x equal to? So if sodium's a limiting reactant, it goes to 0 from 1 mole, and its coefficient was minus 2x. You see how x is equal to half a mole. So we're losing half a mole off of chlorine, leaving behind half a mole. So we can plug x in here, solve for chlorine. We can plug x in, solve for sodium chloride. 2 times x is 1 mole. So we're forming 1 mole of NaCl. 1 mole of NaCl is its molar mass. We have to look it up, calculate it like we did down here, 58.45. So BCA chart makes a lot of sense in a way. Like this is where you can see the initial amount that reacted, the actual excess reactant remaining in terms of what's remaining after the reaction, what's present before, what's reacted, what's consumed in the reaction. And you can see this fall out of a BCA chart. You can see it fall out of dimensional analysis. You just have to be thinking through. The part of the dimensional analysis steps you have to be thinking through are just the fact that we're losing sodium, gaining the product, and once we have produced our sodium chloride, that the reactant's gone. Like that's the part of the dimensional analysis we have to come back to, is the meaning of the numbers. The meaning of the numbers is embedded in the chart, or it's embedded in our mind if we're using it and thinking of those steps as we go along. So the two go hand in hand. The chart is just, I think, takes more writing and usually isn't the fastest way to solve a problem. But the thought of the chart is helpful. I think thinking through the chart and applying that chart when we do a dimensional analysis step is very helpful. So 5 moles of aluminum and excess O2 react together to form Al2O3. What's the yield of the reaction if we get 185 grams of aluminum oxide? Well, notice they didn't give us a reaction because we have to be able to think if we have aluminum, we have O2 combining to form the product Al2O3, that we can write and balance this reaction without it being given to us. So what I might do here is do a 2 here so I can get 6 oxygens, so I can do a 3 here and not have to have a fraction. So I have 6 oxygens on both sides with a 3 O2 and 2 Al2O3, and then I need a 4 in front of aluminum. And so just from what we were told, aluminum and oxygen are reacted together and they're producing the Al2O3. So I was told enough information to write down the reactants and products, and I can work out the subscripts to put the reaction into balance. Now, if 5 moles of aluminum are going to react, how much product should I get? And since the yield's given in grams, the actual yield was given in grams, I should probably calculate the yield of my product in grams. So number of grams of Al2O3 that form when 5 moles of aluminum react is for every 4 moles of aluminum that react, we produce 2 moles of Al2O3. We're actually given the molar mass. Whenever you see a molecule followed by M equals, that's its molar mass, so we don't have to spend time looking up the atomic weights and adding them up. So 1 mole of Al2O3 from what's provided in the problem is 102.0 grams. So sometimes you'll see that thrown into problems so you don't have to spend time just simply adding up the 2 aluminums and 3 oxygens. So if we do that math here, then we would get our theoretical yield is 255 grams. So percent yields, our actual yield, 185 grams, divided by how much we should have gotten. Our theoretical maximum yield, 255 grams times 100%. So that's 72.5% yield. Okay, so that's, again, I think a dimensional analysis that makes sense because we can just in one step figure out the mass of our product we should have gotten, and we're just using then the idea of what percent yield is to solve the problem. So a metal oxide is known to contain 2 cations per anion. So we have some metal, the oxide's the anion. So 2 metals per anion. If the compound is comprised of 5.68% oxygen by mass, which compound below is consistent with this information? And earlier, like we had the thought of, well, look at the choices. Like, is xenon a metal? Xenon's a non-metal. It's one of the noble gases. And it wouldn't form a metal oxide. So on that information, I think you can roll xenon oxide out because it's a non-metal oxide. And then A doesn't make any sense because it doesn't have the right ratio. We're supposed to have 2 of the cations per anion. We only have 1. So it's not even possible. And so then there's really only 2 possibilities. And so then if the percent oxygen is really small, do you think you want the metal to be really heavy or really light? Probably really heavy. So it's probably this one. Now, how do we check? How do we do the math to make sure? Well, one is you could say, well, let's say for cesium oxide, what's the percent O? You can say, well, what's the percent O of this? You would say it's 16 divided by the formula weight of that compound times 100%. You can go calculate it and see if it's 5.68%. Or you could say, if we were wrong, then I might double check to make sure it's not 16 divided by the formula weight of K2O. Now, another approach would be like we solved earlier for the metal chloride, or for the XCl3 problem, is to say, well, I know the percent O for this compound would be 16 AMU for the 1 oxygen, divide by the formula weight of the compound, times 100%, and that's equal to 5.68%. And again, we might get rid of the percentages, 0.0568 as a fraction. We can solve for the formula weight. So formula weight of the compound would be 16 divided by 0.0568. And that works out to be 281.6. So the compound is the metal times 2 divided by O. And so if we lose the 1 O mass, this is the M2 mass would be equal to 265.7. So if we just divide by 2, it would be 132.8. Cesium's 132.9. So if we double check our formula weight, 132.9 times 2 plus 16, 281.8. Percent oxygen, 16 divided by that number, 5.68%. So it's the cesium oxide. And so same basic problem solving approach is just breaking the formula down, thinking how the formula weight corresponds to the percentages. We can mathematically calculate it. But yeah, we can be savvy too, for sure, and roll out some answers. I just want to see if the next question is quick. I know we're up against time, under relatively lengthier problems. So we'll pick up with some more dimensional analysis, or excuse me, some more stoichiometry review problems. There's other review problems in this packet from chapters 1 and 2 as well, so we'll see some sig fig reviews. But if you need more review problems, daily quizzes, and the videos, if you want to see some problems, I have office hours after class 9 o'clock to 10 a.m. upstairs, 2nd floor, 2047 McPherson. All right, see you guys.